At the beginning of Unit 6. Unit 6 is all about exponential and logarithmic functions. And this unit is going to lay the foundation for a lot of concepts that you guys are going to see in later math courses. And the relationship not only between what an exponential and logarithmic function is individually, but the relationship that the two have together. So let's start with learning target 7a. And in this video, we're going to focus on the difference between exponential growth versus exponential decay. By the end of this lesson, we will be able to tell the difference between exponential growth and decay without graphing. We'll actually be able to see this through just the equation itself. And then we will solve some problems that involve compounding annually or compounding continuously and talk about the differences between those two. So what is an exponential function? An exponential function is a function of the form y equals a times b to the x, where a does not equal 0, b is greater than 0, and b does not equal 1. The base b here is a constant number, and the exponent x is the independent variable with a domain of all real numbers. So this is something different. We've seen exponents before, but we've never seen our variable in the exponent. And that's what makes this an exponential function, is our variable is up there in the exponent. Notice that only b is being raised to the x power. A is a coefficient on front, and when we start talking about transformations in a later section, we'll connect that back to our stretches, compresses, and a possible reflection. Now there are two types of exponential behavior, exponential growth and exponential decay. Both exponential growth and exponential decay have what we call a horizontal asymptote. Now what an asymptote is it's a line that a function gets really, really close to, but does not cross or touch. On a graph, we represent this asymptote with a dotted line. Throughout this unit, we are going to see that not only exponential functions have a horizontal asymptote, but we are also going to see that log functions have an asymptote as well. Now let's talk about the difference between exponential growth and decay. Any function of the form y equals a times b to the x, where a is greater than 0 and b is greater than 1 is what we call an exponential growth, and we say that the base b is called that growth factor. So here I've got the equation written out. A is giving us our initial amount. That's what's happening when x is equal to 0. And if we were to sub in 0 for x, we'd get y equals a times b to the 0. But we learned last semester that anything to the 0 power is equal to 1. So we would end up with a times 1, which just leaves us with y equaling a. And so this actually gives us our y-intercept on our graph here at 0, a. Now this base b, if it's bigger than 1, we have what we call an exponential growth. So looking at the graph here, from the left to the right-hand side, the graph is growing over time. This is representing a growth in this function. Our domain here for this graph is all real numbers, because I have all the negative numbers, I can sub in 0, and I have all the positive numbers. But the range, however, is strictly positive numbers. Notice here that this graph just keeps growing over time. It's getting really, really close to the x-axis down here, but it's never crossing and it's never going to touch this horizontal asymptote that we have at y equals 0. So printed on there, I have this blue dotted line representing that horizontal asymptote at y equals 0. Because we have a horizontal asymptote at 0, that's why the range is strictly greater than 0. Notice I don't have an equals to bar there, I strictly have y being greater than 0. Now on the other hand, a function of the form y equals a times b to the x, where our base here is in between 0 and 1. Notice our base did have to be positive for it to be an exponential function, but now we're just considering bases between 0 and 1. That's what we call an exponential decay. And that base b is then referred to as a decay factor. On our graph here, we have the opposite scenario happening. Our graph is starting off really large, and over time it's falling, and it's getting really, 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 really close to 0, but it is still not crossing or touching that horizontal asymptote at y equals 0. Our domain is still the same. Our domain is still all real numbers, because we can sub in all the negative numbers, we can sub in 0, and we can sub in all the positive numbers. And our range is still y is strictly greater than 0, because that's starting really, really high values and getting really, really close to the x-axis down there. Just like before, if I sub in x equals 0, even if my base here is less than 1, anything to the 0 power is equal to 1. So both of these have the same y-intercept at 0, a. Now, of course, we can change the value of a. That's going to change and will stretch or compress our graph here. But if we have no other transformations happening and we're assuming that a is a positive number in both of these cases, our domain and range would start off as all real numbers for our domain, and our range would be y is greater than 0. Let's identify these. So we want to identify if the exponential function is an exponential growth or an exponential decay, then find the y-intercept and the growth or decay factor. So let's look at our first example here. In example 1, it says it's missing the y. It should say y equals, there we go, we'll add it in there. It says y equals 2 times 3/5 all to the x power. Here my a value is 2, and my b value, which is the base of the exponent, is 3/5. What do you guys think? Is this a growth or an exponential decay? So in this case, we have an exponential decay, and that's happening because the b value, which is equal to 3/5, is less than 1. So we call that b value our decay factor, and that decay factor would be equal to 3/5, which is less than 1. Our y-intercept is coming from subbing 0 in for x. Anything to the 0 power is equal to 1, so we just get left with a y value of 2. So that gives us a y-intercept of 0, 2. Just like last semester, we want to make sure we're writing our intercepts in coordinate pairs. Let's look at example 2. So in example 2, we have y equals 1/3 times 9 to the x. Why don't you guys pause the video here and decide if we have an exponential growth or an exponential decay. So in this case, we have an exponential growth because our base here, which is 9, is bigger than 1. So we would call that our growth factor. And to explain why this is growing, it's because that factor is bigger than 1. Our y-intercept is coming from subbing in 0 for x, so I get 9 to the 0, which is just equal to 1, so I end up with a y-intercept of 0, 1/3. Okay, let's look at example 3 here. Well, now I have f of x equals. We learned last semester that f of x and y are interchangeable, and we'll continue to see that in this semester as well. We have f of x equals 1/325 all to the x power. Why don't you guys pause the video here and decide if we have an exponential growth or an exponential decay. So in this case, we do have an exponential decay, and that's happening because our base, which is 1/325, is definitely less than 1, so that's our decay factor. And to explain why it's decaying instead of growing, it's because that factor is less than 1. Now, our y-intercept, we get from subbing in 0 for x. Why don't you guys pause the video and decide on what the y-intercept is going to be. So if we sub 0 in for x here, we'll get 1/325 to the 0 power, which is just equal to 1. My a value, although I have nothing written down, is actually an invisible 1 in front, so our y-intercept is 0, 1, since we end up with 1 times 1. Okay, let's look at our last example of this type. We have y equals 8 times 7/2 all to the x. Why don't you guys pause the video and decide if we have an exponential growth or an exponential decay. So in this case, we do have a growth, and that's happening because 7/2, which is our base, is bigger than 1. So it is written as a fraction. I could rewrite it as a decimal if we wanted to, but 7/2 is bigger than 1, so this is an exponential growth then. Why don't you guys pause the video and find the y-intercept. So our y-intercept we're going to get from subbing 0 in for x. If I sub 0 in, 7/2 to the 0 power is equal to 1. So we get 8 times 1, which gives us a y-intercept of 0, 8. So we're going to continue to talk about the graphs of exponential functions in our next learning target. We just wanted to introduce the concept in here and talk about the difference between either having an exponential growth graph, which would be growing over time, like in the top graph up here, versus an exponential decay graph, which is decaying over time. For both of these graphs, they both have a horizontal asymptote that for the parent function starts at y equals 0. And as well, they both have a domain of all real numbers and a range that is y is strictly greater than 0. In our next section, we are going to introduce the transformations back into these graphs, and we'll talk about how the domain, range, and horizontal asymptote could change depending on what type of transformations we have. Let's talk about how we could model these exponential functions. So one example of modeling exponential functions comes from compound interest. And specifically, we're going to focus on just the example of exponential growth. So compound interest is when a bank pays you interest on both the principal amount of money and the interest in the account that has already been earned. There are many types of compound interest that we could talk about depending on how often the bank pays you the interest. Some examples could be quarterly, which would be once every couple months or 4 times a year. We could have compounded monthly, compounded daily. We're going to talk about what 2 types. The first will be compounded annually, which means we are only earning interest once a year. And then we're going to talk about the complete opposite of that, which is compounded continuously. And compounded continuously is not the same as daily. It's actually compounded on every second of every day. So let's start with compounded annually. We have the equation A of t equals p times the quantity 1 plus r to the t. Let's talk about all the pieces of this. A of t is representing the final amount of money at a given time t. P is the principal amount of money, or our initial deposit into the bank. R is the interest rate, and we have to remember to convert that to a decimal. And then T is the time in years for this scenario. Now, on a learning check, I will give you guys the equation for compounded annually, as well as the equation for compounded continuously, but I will not label which type is which. So it's your guys' job to understand the different pieces of each of these equations and understand in what scenarios we use compounded annually versus when we use compounded continuously. So let's look at an example of compounded annually. It says that we invested $2,000 in a savings account that pays 2.35% annual interest. What will the balance be in our savings account after 15 years? We want to make sure to write out the equation before we type it into our calculator. So on problems like these, we will need a calculator to determine this. It's not something we can do in our head, but we are required to write down that equation. If you guys just write down the final answer that you get out of your calculator, you will be earning no points on these. I am much more interested in you explaining to me that you understand the formulas and that you know how to sub them in from there. So let's talk about how we would set this up. So in this case, our principal amount of money that we're interested in investing is the $2,000. We have an interest rate of 2.35%. Now we need to convert this to a decimal. We were technically taking the percentage and dividing it by 100, which is equivalent to moving the decimal places 2 places to the left. So 2.35% is equivalent to 0.0235. If I want to check that, I can check and move the decimal places 2 places to the right, and I would end up with 2.35. Or, in your calculator, you can take 2.35 and divide by 100 to get the decimal interest rate. And the last thing we need to identify is the amount of time that we're investing this money, which is 15 years. So now let's set up our equation. We want to find A of t, or in this case, A of 15, since we're investing it for 15 years. That's going to be equal to the principal amount of money of 2,000 times the quantity 1 plus our interest rate converted into a decimal, so 0.0235 raised to the number of years, which would be 15. This setup I need to see on your paper in order for you guys to get credit or get any points on a problem like this. From here, we'd then use our calculator to calculate it. So, from the home screen of a calculator, we're going to go to A for calculate. I'm going to start typing in with the 2,000. Now, I don't type in the A of 15 because that's what I'm trying to find. I want to type in the expression that I want the calculator to simplify for me. So I have 2,000 times the quantity, so times, then I'll need parentheses, 1 plus 0.0235, and then I want to arrow out of that to get outside of the parentheses, and raise it to the 15th power. So I need to use the caret symbol here. That will get me that box as an exponent. And I'll type 15, and then from there, I'm going to click enter. So we ended up having, after 15 years, $2,833, and we'll just round up to have to the hundredths place, so 66 cents in this case. So from here, I'm going to go back to my paper, write down my final dollar amount, which was $2,833.66. And we can always double check that just because I don't have the calculator up at the same time. But yes, that matches from there. So again, on problems like these, I am much more interested in the setup, the equation. Of course, I am testing to make sure we understand how to type this in correctly into a calculator, but the setup here is absolutely necessary in order to get any points on a learning check. Okay. Let's talk about compounded continuously. So compounded continuously is what happens when our money is constantly earning interest on the money that's invested in the bank. Theoretically, it's the best type because I'm earning interest more often than any other type. We have a similar equation. We still have A of t, which is the final amount of money after any time t. P is still our principal amount of money or the initial deposit made. We have this E here, which is approximately 2.718281. It is an irrational number, so it does keep going. It's called Euler's number. It's a mathematical constant that's actually built into our calculator. And this is probably the first time you guys are ever seeing it in a class. You might have noticed the button on the calculator before, but it's going to be something that's going to come up a lot in this unit. So Euler's number, or E itself, is our natural base, and that's going to come up a lot not only with exponential functions, but also when we start to talk about log functions as well. R is still our interest rate that again we have to convert to a decimal, and T is our time in years. So let's look at our example for this one. This time we're investing $2,500 in a savings account that pays 2.75% interest compounded continuously. So if I scroll back up to the prior example, notice it says it pays annual interest. So that's telling us the difference between compounded annually versus compounded continuously. And the problem does need to specify. I can't just decide on my own. I would need it stated in the question for me to know which one to be computing. We're then asked, what will the balance be in the savings account after 15 years? So why don't you guys write down what your principal amount of money is that we're depositing into the savings account. Also write down your interest rate converted into a decimal. And lastly, write down the amount of years that we are investing this money. Okay, so let's check that. Our principal amount that we're investing is $2,500. Our interest rate is the 2.75%, which to convert to a decimal, I'm going to divide by 100, which is the same as moving the decimal 2 places to the left, so 0.0275. And then we're investing it for 15 years. Okay, now we need to sub this in. So we are interested in figuring out what A of 15 is equal to, since that's the amount of years that we're investing. That's going to be equal to our principal amount of money of $2,500 times E. So I'm going to literally write down E, that is representing our mathematical constant there. E to the 0.0275 times 15. And in the equation, R times T is the whole exponent there on our base E. So I need to make sure all of that is written in an exponent. And make sure your writing is clear so that it's clear to me as a grader that 15 is up there in your exponent and being multiplied to that interest rate in a decimal. This setup is earning us the majority of the points on this problem because we're understanding the fact that we use the compounded continuous formula and how each one of these moving pieces gets substituted in. From here, we're going to go to our calculator and sub it in. So we have 2,500 times, now E is built into our calculator. It's on the left-hand side here. It says that E to the X button. When I click it, notice I get a bolded E. Down below in the alphabet, there is an E, but that's not programmed to be our mathematical constant of Euler's number of 2.718281 and so on. So I don't want to use the E down here. That's for something else if I were to store a variable later on in a different class. I want to use the built-in mathematical constant, so I need to be using this e to the x button. It automatically made the exponent on it, so I'm going to type in 0.0275 times 15, and all of that is up there in the exponent. If I click enter, we find out that that is equal to $3,776.47 if we round, since that would not be rounded up. So from here we can go ahead and write that down, and our amount of money after 15 years would be $3,776.47, I believe. Let's just double check that with the calculator. Yes, that is correct. Okay, so in this first section of Unit 6, we learned about the difference between exponential growth and exponential decay, and we also learned about compounding annually versus compounding continuously.